Hello everyone, welcome to lecture 6. This is the first part. In the first part, we are going to talk about the derivatives. What is the definition and how to calculate the derivative. In the second part, we also talk about the different rules and properties when we calculate the derivatives. So now let's look at the first part. Now, what is a derivative? So remember in the first class, we talked about the definition of a derivative. So imagine we have point x0, and given the function f of x, now we have the evaluation of this point as the value of this function. So this is a arbitrary point, and we would like to know the derivative. For example, if we draw a curve, then this is the point, this is the coordinate of this point, and we'd like to know the derivative of this point. And the derivative of this point is the slope of this tangent line. So this is a tangent line. Now, how do we calculate the derivative? We imagine there's another point which we add a bit of a distance. Now it becomes x0 plus delta x. So delta x is a ever so slight difference in x0, and then the corresponding evaluation of the function x0 plus delta x, right? So this is the other point in terms of its coordinate. So we would then move these points slightly and then gradually towards the original point, so that we approach the limit when delta x goes to 0, right? So in definition, this is what it looks like. So we see that the derivative of f of x, right? So we see that this is how we express a derivative, and this is for any arbitrary point x. Now the derivative is defined as the limiting condition when h goes to 0. So h is the same as delta x, and we want to know what would the slope be when such limiting condition happens. So what is the expression? It will be the slope of the line that connects these two dots, right? So we have the h, and this is the distance, and also the difference between the y evaluations. So f of x plus h, the new point, and then the old point. So this is the definition of the derivative. Now we see that this derivative exists for an open interval a to b, right? So it's just graphically it's like this from a to b. If the derivative exists within this interval, then we can say that this function itself, this function f is differentiable, right? Differentiable. So it can be differentiated everywhere across the range. So what's special about this is that if we actually, actually draw another graph, and this is the other point. So this is the original point, point 1. This is the other point, point 2. So if we were to draw a line that crosses this point, this is the point, the line, we can call it as a secant line, right? Secant line. And then this line is what we care about, is the tangent line. We want to know the slope of the tangent line, and we're actually moving the points. We're actually making the secant line approaching the tangent line so that they eventually overlap when the limiting condition happens, right? So there are a few different interpretations of a derivative in different contexts. So we already know the first interpretation is the slope, right? The slope of the tangent line, right? So the slope of the tangent line, that's directly from the graph we have in this case. Now the second interpretation is the instantaneous rate of change, right? So because we talk about how fast something changes, how fast y changes when there's a change in x. So derivative measures how fast, when we are looking at this point, this specific point, x0, right? And how fast the slope changes the y changes. So the slope gives us sort of a sensitivity in terms of how fast y changes. Now the third interpretation is the velocity. Velocity in the context of a moving object. So say we have, so this is the, for example, the position of a moving object, like each position, each time point, we are at a different location. And the way we would calculate the velocity is just to take the derivative of the location of the object, right, of x, with respect to the time points we have. So this is the formula we have for calculating the velocity, right? So okay, so that's basically different interpretations we have in terms of derivative. Let's move on. So here, the a bit more detail on the instantaneous rate of change. So we know how to calculate the average rate of change. So the average meaning we are changing f, right? So this is the old value of y, or f of a, and this is the new value of y, or f of a plus h, right? So we're taking their difference in terms of the change of y, right? The change in y, and we want to know what is the average in the difference in y. So now we are actually taking into account the distance between the new point and null point in terms of the x-axis, and then this is the average rate of change, like how fast it changes. Now, if we take h to 0, which is to say that we are adding a limiting condition, then this is what we have in terms of the definition of a derivative, and it also implies that we're actually looking at instantaneous rate of change. We are shrinking the interval itself so that h will be infinitely small, and we're looking at the rate of change that is actually instantaneous at the specific point, which is a, when x equals to a. All right, so by definition, the way we calculate derivative can be divided into 4 steps. The first step is to, so all the steps are just plug in and play, right? So calculate f of x plus h, then the numerator, then the whole quotients, and then add a limiting condition as the last step, right? So we can actually express the derivative in different ways. So this is the one we can express y prime dy over dx, df of x over dx. So that's these are equivalent ways of expressing the same derivative. Okay, so this is a formula for common derivatives. Now it's also a list of the formulas we will commonly encounter in future lectures. So first one is the common function. If the constant function, if the function is constant, that means it's a flat line. Then the derivative is 0 because there's no change in the value of y, right? It's always 0, always flat. The power function, the way we calculate the derivative is to move this power, right, to the power of n. This is nth power, right, besides x. So this n times x to the power of n minus 1. So now this becomes 1 less. So this is just something to get you familiar with. Exponential function, if the base is e, then if we take the derivative, it's actually still itself, right? If the base is b, then this is what we have. So because we have this extra ln b here, right? So this is something to keep in mind. Logarithmic function, if we're taking the derivative of ln of x, then it's the inverse, it's y over x, right? So this is the results. Then if the base becomes b, then we have extra term here, 1 over ln b, right? So this is something to keep in mind. If we look at the sine and cosine functions, so the derivative of sine x becomes cosine x, and the derivative of cosine x becomes the negative of sine x. So this is special negative sign to pay attention here. Okay, so now let's look at a few rules we would commonly encounter in practice. So the first rule is the constant function rule, which we'll talk about. So you can see that let's look at the first and step one. So if if of f(x) is a constant function, then it becomes naturally the derivative is gonna be 0 because it's a constant, and that applies for this one as well because pi is also a constant. Secondly, the power rule. So if we look at this one, right? So this is saying that the f of x equals to x to the power of 5. Then in this case, what we can do is to plug in the formula, and f of x becomes 5 times x to the power of 5 minus 1 becomes 5x4. Right, so this is the first one. Now look at the third question. So if y equals to t to the negative, to the power of -3, then we can say dy over dt, which is another way to express derivative. It becomes -3 t times t to the power of -3 minus 1. And that gives us -3 times t to the power of -4, right? So so you can apply the same rule and work out for the b and d as well. All right, so let's look at exponential functions. So we know these two rules already, and this just to remind ourselves. This one, why we have let me see. Okay, right. So this is the special rule we have in terms of the derivative of an exponential function when the base is b. And why is that the case? Is because now we have b to the power of x, right? So this is the exponential function with the base b. Now we know that this is already known, right? So e to the power of knowing x becomes x. So this is from previous class, and we know that if we are taking both sides, then this becomes itself. So so now b to the power of x becomes e, right? And then ln. So assuming this is x, then it's gonna be ln bx, right? So and what we're doing is moving x, right? Here now we have e to the power of x ln b, sorry. Right, so this is called the changeable base formula for exponential functions, and this is something just to keep in mind, and it may come in handy when we actually solve the problems here. Okay, so there's one slight caution to pay attention to. So here, the derivative of e of x is not actually, so we cannot move x below beside e because it's not a power function, right? So we can only do this when it's a power function, but when it's a exponential function, then it stays itself if the base is e, right? So now let's look at one example. So for example, this one, and we are looking at the derivative of g of x. Now we can say the derivative itself becomes 2x, right? So this is what we have, and then we have an extra ln b. So we are going to time ln 2. So this is for the first part. The second part, 3x ln 3. Right, so just plug in the formula and we have the results. Okay. Next, we have the derivative. Let me see. Okay. Right. So we have the logarithmic functions. So logarithmic function, when the base is b, then we need to time the extra 1 over ln b. So that's something to keep in mind. And this is again because that we have ln base b, x is actually can be re-expressed as ln of x divided by ln of b, right? And if we are taking the derivative, it's actually saying that this is constant, ln of b times ln x, right? So this becomes a constant. So a constant stays as a constant when I take the derivative, and this becomes 1 over x, right? Because of this rule. All right, and x, something extra to pay attention to. Ln of a over b can be expressed as ln of a minus ln of b. And this one we can actually, if this to the power of p, then we can move p beside ln. So p times ln a. All right, so let's look at one example. For example, this one, we can find the derivative of y equals 2. Now, first one would be 3ex because it's an exponential function, right? Stays as it is. Plus 5 over x because it's just ln of x. The derivative will be 1 over x. Okay, so now that's for the logarithmic function. Next, we have the sine and cosine functions. So again, this is rule just to remind ourselves. And something extra is that we have this generalized form, which means that if u itself is actually another function of x, right? So u is another function of x. Now, when we take the derivative of this guy, sine of u, with respect to x, right? So meaning x goes through u of x, then u becomes a variable of the sine function, sine of u, right? Or we can express this as sine of u of x. So this is just a series of transformations, so a series of functions applied here. Then when that happens, we need to take the derivative of each one. So derivative of this of sine u respect to u and derivative u with respect to x, right? Step by step. So the first one, the sine u becomes cosine u in terms of derivative, and this is the second part. And these two parts actually should be multiplied together. So this is the chain rule, right, of derivative. Similarly, we have this as well. So the first part, the second part multiply together. All right, so this is just some exercise. Let's look at some exercise. The first one, it will become, so now we have the function here. Now the first part is gonna be cosine of x squared because of this rule, right? So sine of x becomes cosine of x in terms of the derivative. The second part, we need to take the derivative of with respect to x of the function x squared because now u becomes x squared, right? We need to take the derivative, and that gives us cosine x squared times 2x based on the power rule, right? So then reshuffle a bit, we express this 2x cosine x squared. So that's the derivative we have. All right. And the second question, we can apply chain rule as well, as we mentioned, similarly. Okay, so that's it for this class, and hope to see you in part 2 of this lecture. Thank you.